There we go. Yes. Good morning. Welcome to today's class. Before I start, I would like to sample. How many of you are PhD students at IITM or elsewhere? How about others? They are MTech students, or how many of you are MTech students at IITM? How many of you are project students at IITM? Is there anybody who is not from IITM? I didn't call you. So everybody is from IITM. Is that right? Thank you. I'm glad you're all here. And I would like to have a chance to talk to those who are online. Hello, good morning. Do you hear me?
They can't respond, but they hear me. They can't respond, but they hear me.
I would like to encourage all of you online to stop me if you have any questions. I'm told that you can type in your question in the chat box, and I would like to have your reaction as we go by. Please don't hesitate to ask questions at any time during the course of the talk. Thank you all. Same thing applies to you too. So yesterday we talked about what is data science, what is AI, and various facets of AI, data science, and the interrelations and so on. Along with data science, we also keep talking about big data. Who creates the big data? Where does it come from? What is big in big data? That's what I'm going to talk about in the first part of the lecture. And in the second part, I'm going to talk about some of the surprising results from geometry that often arise in high-dimensional data sets, which is counterintuitive, and we need to be able to understand so that we can address some of those issues later when we are going to be doing problems in data science. So those are the topics for today's discussion. So we already talked about it yesterday. In the early days of astronomy, data was collected by humans by handheld telescopes. Data was very sparse. In meteorology, they send balloons. Each balloon is very expensive. The amount of money that they have allocated to balloons is limited. So they can only get very sparse data. The balloon goes up, it bursts. It's a destructive way of measuring things. And we only get data along this track. Along with balloons, they also collected information from ships, aircraft. Even though there are many ships, there are many aircraft going around. Still, the expanse of the three-dimensional world is so big. The amount of data that we used to collect from these sensors were very limited. Data was very sparse. I already alluded to yesterday, thanks to advances in sensor technology, wireless communication, large-scale storage devices, computers with increasing power, and it is estimated that the amount of data that we collect doubles in every 2 to 3 years. Doubles in every 2 to 3 years. So this is where the big data comes from. The amount of data that we are collecting. And why? Who is responsible for that? We have replaced the human sensors by satellites. Satellites keep tallying at the Earth 24/7. Radar keeps tallying at the Earth 24/7. They can very finely sample different parts of the atmosphere, the land. So the amount of data collected from these sensors, looking at the Mother Earth and the atmosphere 24/7, is enormous. And that's one source where big data often arise. So what are the examples of big data? We are not the only one in meteorology, geosciences dealing with big data. Speech signals, radar signals. Radar signals are different types. There are different types of radars. There are radar, terminal Doppler radar, military radar that's particularly meant for military purposes, and so on. Hyperspectral images from satellites. We depend on satellite to be able to get visual images of various aspects of the Mother Earth. Genome analysis, text documents, fingerprint analysis, facial expression, product data. So you can see big data domain, data science domain is very large, very big. And ultimately, whomever is interested in data science have to be concerned with the domain-specific knowledge to bring to bear on the problems of interest in that particular domain. I would like to give you some broad view about the ways in which big data arrive. So let's take a very simple example of a fingerprint. Some of you might think, gee, he's starting the fingerprint. I'm a meteorologist. I'm interested in geos variables and so on. Please understand what meteorologists are using. They are using neural networks. Neural networks where they first found out in electrical engineering. Are you with me, please? That's right. So even though you may be working at atmospheric sciences, you need to know the origin of the tools and techniques that arose. Many of the tools of interest in AI arose within the halls of electrical engineering and computer science. So to be able to give you an idea of we in geosciences are not the only one dealing with big data. There are lots of other people. So if you understand how they solve that problem, that will give you an idea for you to be able to solve the problem. Are you with me? Please understand. The neural networks were invented by computer scientists. But we are trying to apply that. So it is good for us to be able to understand where those applications came from. How did they solve their problem? What is the similarity between my problem and that problem? Is there a way to translate the solution process from area A to area B? All of you, I want to give you one more thought process. Why? I just don't want you to narrow down your viewpoint. You're all PhD students. I would like to be able to have a broader view. For example, how many of you know, Calvin, how many of you know data assimilation? But even if you didn't know data assimilation, that's all right. Calvin filtering technique, how many of you have heard of it? How many of you know the details of Calvin filters? You have heard of it, but you may not know the details. But I want to tell you something. Calvin filter was invented in 1960-61. Calvin was an electrical engineer. By the time the meteorologists found that Calvin filter could be used within meteorology, it was 1985. So Calvin filter was known as early as 1960. In fact, I was a student at the Institute of Science in the late 60s, early 70s. The Institute of Science had invited Calvin. So I heard Calvin filtering from Calvin himself. He gave a talk for 3 days. Why am I mentioning this? I want you to understand that methodologies developed in one area, they slowly migrate into other areas. It takes time. Are you with me? But the earlier you know the methodologies other areas use, the quicker you'll be able to see the potential for its applications. So that's the reason I'm going to talk about some of the problems that are not directly related to geosciences, but the tools and techniques were developed within this context. And that's what folks in meteorology, folks in geosciences are trying to catch. With me? That's right. So, fingerprint analysis. Our fingers have lots of ridges. If you do hard work, they all go smooth. But nevertheless, we all have ridges. And the fingerprint is supposed to be a good indicator of who you are. It's a signature of who you are. So let's talk about how the fingerprint is done. So in order to be able to analyze fingerprint to understand who you are, to let entry into a gate, you have to authenticate. So you press your fingerprint. The other database that contains all the fingerprints of people who are supposed to be legally inside. So you press your fingerprint, then it checks and then say, yes, This is who you are, let you in. So now let's talk about, so that the computer that makes a decision that this person with this fingerprint is indeed authenticated to enter. So what does it mean? I have to computerize this aspect of fingerprint classification. That means a fingerprint is an analog device. I have to digitize it. So one of the aspects of computerization is to represent objects digitally. So how do I represent fingerprint digitally? So there is a screen. The screen may be of size, resolution 64 by 64. 64 by 64 pixels are going to get a picture of your fingerprint in black and white. Total. And so 64 times 64 is 4096. So one fingerprint has 2 to the power of 12 pieces of information in the form of pixels. So let's assume there are 2,000 people working in IITM. IITM wants to keep track of all the PhD students. When do they come? Because they pay money, right? They have to keep track of who is where and so on. They don't take attendance like the old ways. Now they all have biometrics. Are you with me? Now, this is just an example. Is 64 by 64 enough? No, I may go for 256 by 256. 256 times 256 is much larger. So I'm representing one fingerprint by a vector of size 2 to the power of 12. In case I have a digitizer of size 64 by 64, 2 to the power of 12 is large. It's not very large. It's not too big, but big enough. So if there are 2,000 people working in IITM, each person is represented by a vector of size 2 to the power of 12. So 2,000 times 2 to the power of 12. 2 to the power of 12 rows, 2,000 columns. I get a matrix. Matrix is stored into the computer. You come in at 9 o'clock. Here, things don't start before 9, right? Come on, guys. USA is very cold. The temperature in Oklahoma, the high temperature in Oklahoma has been 22 degrees Fahrenheit. The university starts at 8 o'clock. Okay. So, well, that's a side case now. So you enter, you get an entry or not. Yesterday I talked about classification problem. So most of the classification problem have a digital representation of data in the database. And the data is represented in the form of matrix. N is the number of objects. M is the representation of each object. There are 2 parameters, M and N. N depends on the size of the organization. M depends on the details with which I want to represent a human being. It could be your face, it could be a fingerprint, so on and so forth. Everybody with me, please. So who makes the data big in big data? You. What is the resolution you want? The 64 by 64 resolution is a coarse resolution for purposes of taking attendance. That's good enough. Now let's look at your face recognition problem, color images. Why am I talking about these things? Please remember, deep neural network, every one of you are interested, but deep neural network were developed with respect to classifying cat from a dog, the picture of a dog from a picture of a face of a human. So that's where I'm taking this too. So human face, let's assume we are going to have a colored image. There are 3 frames, RBG. In each frame, I'm going to have a 256 by 256 grid. 256 by 256 is 2 to the power of 16. Everybody should know 2 to the power of, what is 1K? One in computer science, we work with the base 2 as well as base 10. Outside of computer science, you all work with only base 10. So you talk about memory. I have 1K memory. What is 1K? 2 to the power of 1024. 1024 is 2 to the power of 10. That's right. So what is this? So 2 to the power of 10 times 2 to the power of 6. What is 2 to the power of 6? 64. So in one frame, I have 64,000 pixels. There are 3 frames, so 3 times 64,000, that's very close to 200,000. That's one face. But human face, we don't look the same in the morning. You don't look the same when you're tired, when you are joyful, when you're grumpy. You don't look the same this way, you don't look the same this way. So it has been found by people who work in face recognition that you need at least 10 poses of a human face to be able to use face as a signature for recognition. All of them? FBI is the equivalent of CBI here. They would like to have a database of criminals. Okay? So think of it now. One person's face, one shot is 3 times 2 to the power 16, 10 such poses. So one person is represented 10 times, 3 times 2 to the power 16. That's a lot. In countries like India, I'm sure CBI has millions of records. FBI has millions of records. All with me? That's right. That's right. A crime has been committed. They tell who the person might have been committed. Then they call an artist. The artist gives you, based on your description here, this cheek, there, this hair, there, this face, and so on. I didn't take a picture of him. So the artist creates an image of the would-be person they are searching for, and the FBI, within 2 days, they say, I have identified the person. I have caught the person. Are you with me? So there's a database, there's a suspected individual. I may not even know. I may not even have an image of the suspected individual. Based on the sketches, I could even identify that. Database problem. Such problem. Large data representation. Are you with me, please? So who makes the big data? We. Why do we do that? Because we want to have increasing resolution to be able to represent the objects of interest so that we can make meaningful discussions, meaningful analysis of the data that we are called upon to do. So the face variation depends on the illumination condition, different poses, facial expression, time in a given day, and so on. Okay? So the face recognition database is much larger, much bigger. Hyperspectral images from satellites. Many of you, I have talked to many folks, and satellite data analysis is an important segment within IATM. You may be interested in using satellite data largely for the purposes of meteorological applications, but I'm going to talk about the nature and type of images that satellite brings in. So they are used for geographical scenes. For example, there was an earthquake of magnitude 7+ in Turkey, Syria. How do they get the image of that through satellite? Instantaneously, they get the nature and extent of the damage. So satellite pictures are very useful. They're used to catch mountains, snow caps, green fields, and they are able to capture the area of pure water lakes, because pure water is in great demand these days. So satellite images are used for several different purposes. So what is their basic idea? Use the wavelength from 350 nanometers to 3,500 nanometers in that range within the electromagnetic spectrum. This includes the visible and the infrared regions. The visible region is from 380 to 700. Infrared is from 700 to 3,500. Microwave region is 1 millimeter to 1 meter. This range is divided into small bandwidths of length 5 to 10 nanometers. And in each of these small bands, I'm going to get a picture. So if my range can accommodate 10 such bands, I'm going to have one image from each band. So that's going to be 10 stacks. Each stack is a rectangular stack, just like RBG. In the case of RBG, the stack is depth 3. In this case, the stack depends on the number of sub-bandwidths within a given range the image is made up of. So each spectral image band creates an image of the scene. So an image is a 3D object, which is called the hyperspectral image cube. Is there a question? Hyperspectral image cube. The image information in each bandwidth reside in the 2D. It's a collection of 2D. The depth is the one that makes. So given a pixel in the vertical dimension provides a spectral radiance. So the image is xy are the physical domain. S represents the number of slots in the bandwidth. Are you all remembering? So if nx is the number of pixels in the x direction, if ny is the number of pixels in the y direction, and if ns is the number of bandwidth, the size of the image is going to be nx, ny, and ns. And that can be very, very large, depending on the resolution that you want. So if you are interested in trying to develop algorithms, when you develop an algorithm, when you want to publish papers, you can use your own data. But the reviewers might often ask, can you test your algorithm on a standard database? In other words, I didn't try to concoct an algorithm for the special data set I have. If your algorithm is general enough, it should be applicable to several databases. So you should be able to represent the behavior of algorithm across various types of data. So Caltech has data set that you can use. Purdue has a data set, and these are some of the available data sets that you could use to be able to prove the efficacy of your algorithms if you are interested in trying to develop your algorithms. Text documents. I want to digitize a text. Yesterday I talked about how do I compare two programs to see if they didn't copy. How do you test if I submit a paper, what percentage of the paper may be thought of being plagiarized? Do they lift paragraphs from other papers? That can make a problem in the day of being able to cut and paste. Generally, that happens more often than not in conference papers. We copy from our old paper itself. And allowed many conferences are very sensitive about that. So I want to be, I'm not here talking about the ethics of copying things from your old paper to new paper. I'm not interested in judging that. I'm interested in the task of being able to decide how you evaluate the amount of plagiarization in programs, in newspaper articles, in papers. So what the idea? Text is an analog device. Printer, pictures, so on and so forth. I need to be able to digitize that text. Because anything to be done in computers has to admit a digital representation, much like a human face, much like a fingerprint, much like a satellite image. There, they are based on the pixels. Here, there's no pixel to talk about. So what is the basis for digitizing a text? Let's take, for example, English language. How many words are there in the English language? Very many. In fact, I have a dictionary that I bought 25, 30 years ago. It is this thick. I use it for occasionally for references. So that's for the fun of it. I haven't counted how many are there, but there are well over 1,500 pages. In each page, there are 3 columns, and you need a microscope to read them. You know that, right? The practical thing. Incidentally, these days they don't print dictionary. Everything is in disk. These days they don't print encyclopedia. When I was in college, there are people who say, hey, I need an encyclopedia for my house. I don't know whether your parents have an encyclopedia at home. We used to display the encyclopedia so that anybody can see, yeah, I have an encyclopedia. These days, encyclopedia is not printed. It's all in the desk, digitized. So let's talk about how you digitize text. So you have English language words. So you alphabetize all the words in the English language, and that is one column. That's the leftmost column. The text Shakespeare, just as example, Othello. Othello is a drama by Shakespeare. You count the number of words, number of occurrences of each word in Othello. Are you in the place? So Othello can be represented by a vector with integer, with a non-zero entries. So what do? If the word that occurs 200 times, you put a word, you put the number 200 against the word that. So Shakespeare is going to be represented by a vector of non-negative integers, where is zero? If a particular word Shakespeare did not use, the number of occurrences of the word is zero. So the entries are either zero or positive integers. Each integer represents the number of times that particular word has occurred in Shakespeare. It doesn't have any information about where it occurs, in what context it occurs. Please understand, a language has two components. One is the syntax, another is the semantics. So I'm simply interested in some parts of the syntactic component. The syntactic component being the words. The sentences, you need a grammar. Once I have sentences, then there's a meaning. The same word, the same sentence may have several meanings depending on the context. So a language has a semantic component, syntactic component. One part of the syntactic component is the distribution of the number of words. Computer scientists over the past 50 years have found out the best way to digitize text is to look at the vector, where each entry in the vector denote the number of times a particular word in the alphabetical order occurs. Are you with me now, everybody? How you convert your text into a digital form? So a program. So let me think about a program now. In programming language, there are common words everybody has to use. If, for, yen, so on and so forth. So everybody has to use that. If you're doing mathematics, you need plus sign, minus sign, equal to, so on and so forth. And when you state a theorem, if A, then B. A, if and only if B. You cannot invent it. So those things have to be not included in trying to compute the plagiarism. So how do we check for plagiarism in programming? You have to invoke to your own variables, right? If two people picked variables for their own program, there is no one reason why you and I should pick the same set of variable for the same quantity throughout. But again, so there's copy, there's dumb copying, right? What is intelligent copying? I'm not saying you should copy. In intelligent copying, it's not copying actually. I talk to you, you show me. Okay, then I sit down and try to do it myself. If I did it myself, there's no one reason I should concoct the same variables as you do. What is the dumb way? You give yourself in the hands of the police. Are you right? Using the same variables. So these programs, what do? They given two programs, it has a word count, common word that are common to every program, and that is drop. It counts the number of variables this program has, this program has. If there's a large similarity between these two, the program doesn't decide they have copy, it kicks it out and tells the instructor, it looks like these two guys are suspicious. Are you okay? I have taught programming courses. In my days, my policy was the following. If we found out that two people copy, I don't want to be a judge, I want to be a teacher. Both of you get 0. Who am I to believe? Each one will come and swear. He did copy, or she did copy. The law should be fair and uniform, right? Okay, good. That's a side story. So each text is represented by a vector of frequency. So what is the frequency? what is the total number of words in Shakespeare? What is the particular occurrence? You divide each occurrence by the total number of words, that's frequency. So you can either work the frequency, in which case it will be real numbers, or you can work with the integer variable themselves. So here, what is the idea here? I have a matrix of size, matrix number of rows are m. M is the number of text. M is the number of text. So I can talk about a collection of text represented digitally. I can compare which of them are similar to each other based on this digital representation. Based on this digital representation, text document process. In today's world, what is the basic thing? Fake news. Okay? How do you identify the news is truth or fake? That's a difficult problem. You just throw something into the net and everybody forwards it. They won't even read it. Do we do that? We are all culprit of that too, to some extent. So there are lots of data science related questions within the context of processing text documents. So here are some text document sources in the world of medicine, the world of space, in the world of religion, and so on. So you may want to use some of these databases. Now let's come to geosciences, which is half of the people who are here. I'm hoping all the people here are geoscientists, right? Come on, if there's a non-geoscientist, please raise your hand. What are you? Huh?
Computer science.
Well, good. That's good. Is there anybody else? Atmospheric sciences? Ocean sciences? So I'm talking to reasonably homogeneous computer scientists like me. I'm a computer scientist. Applied mathematics. So let's talk about the atmosphere. Atmosphere consists, geoscience deals with atmosphere, ocean, pure water mass, deserts, so on and so forth. You can add things to it. A typical field variable represents three space and one time. So it's f of x, y, z, and t. The radius of the Earth is roughly 4,000 miles. In the United States, we still use miles and feet and pounds. Everywhere else in the world, it is kilometers, it is kilograms, it is centigrade. I having grown up in India, I can go from back and forth, so I have no problem. So the equatorial circumference is about 25,000 miles. The surface area for pi r square is about 500 million square miles. Roughly, take it away. Let's assume I want to represent a field variable on the surface of the Earth, 1 grid point per square mile. That's ambiguous. What is the resolution of the good models they use? The maximum model I heard it is about 12.5 kilometers. Right? Correct. Models used to be 100 kilometers, then it came to 50 kilometers. At the University of Oklahoma, we have an ARCS model that can work in 2 kilometers. They would like to go to 0.5 kilometers. They can do it, they know how to do it. It's simply computers, storage, computer time. So let's pretend that I want to have the field data represented on the surface of the Earth, 1 data point per every square mile. So how many do we need? 500 million. That's just on the surface. Then atmosphere. What is the end of the atmosphere? Is about 100 miles. What is the active? About 10 miles. You may differ with me, but that's all right. If it is 12, if it is instead of 10, if it is 20, so be. I don't care. So let's take 10 as a starting point. So how many levels do I want to consider? 50. Some of the models, they consider 50. So there are 50 concentric shells. On each shell, I'm going to have 500 million points, 50 times 500 million for one field label. So it is not that I don't know. I can generate this. With me? This is for a global model. Your Monson model, is it a global model or regional model? That's probably a global model that feeds into your regional model. Because I want to do things on a finer scale. All of it, you take the west of India, east of India, north of India, south of India, and you chunk your space, and you have the boundary condition coming from the global models, and then you do a final grid of that. So 12.5 kilometers is your grid size. That's reasonably big right now. Can we go to 1 kilometer? Sure. And what is the price you have to pay? The big data even becomes bigger. And how many field variables? In the case of face recognition, it's only one pixel. Red, green, and blue. But in here, pressure, temperature, wind, three components of the wind, humidity, and what else we want to. So the number of field variable times the number of grid points. So geoscience is one area. Big data gets very big in a hurry. In a big hurry. Okay. You can make it as big as you need. You can make it as big as you want. So I already just talked about that. And then I didn't talk about the timing slope. Do you want daily data, hourly data, seasonal data, decadal data? Okay. It's something you already know. I just want you to tell that geophysical sciences is notorious when it comes to being able to generate big data. I'm not talking about handling big data. What's the topic today? The sources of big data. Where big data arise, who makes it big, how big can we make it? All of it, I just want you to think about how you folks in meteorology or geosciences do, how folks in other branches handle, generate big data, and all big data problems have, if they are not identical, they have something in common. So what's my suggestion? Talk to your electrical engineering folks. Talk to your computer science folks. They may not understand your lingo, but try to understand the problem. Radar. United States has 50 states, as many of you know. Alaska is separate. Hawaii is separate. The rest of the 48 states are contiguous. The entire 48 states together is covered by a network of 142 radars. Yes, severe weather is going from southwest to northeast. As it crosses the borders of each state, there is a handoff. This radar network to that radar network to that radar network. There is absolutely no gap. There's a lot of overlap. So that any serious system that arises in any part of the USA can be very meticulously tracked. For the amount of data it creates, 142 radars. And then there are 11 in Hawaii and Alaska together. There are well over 200 airports. Each airport has a terminal Doppler radar. Okay? So you can see the total amount of information about the atmosphere and its properties coming from all the radar network together. In fact, there is a National Center for Environmental Information that's in North Carolina. They have a library of all the data. So I want to be able to understand certain properties of a tornado that happens in 1952. Sure. I want to be, likewise in Miami, they have information about every hurricane that happened in Pacific and in Atlantic. Pacific. They're very huge database. You can only imagine how long the database of hurricanes and weather-related radars. So here is something for my electrical engineering friends, how the bandwidth available for radar is finely chopped so that different applications can invoke to different bandwidths. Military, thermal Doppler radar, weather radar, they all work in different bandwidth in order to minimize anything, just like radio network, satellite, TV networks. So now come a bit more about satellites. I'm sure you all know this. Russia launched the first satellite Sputnik in 1957. Weather satellite was first launched in 1960. There are well over 1,100 active satellites today. Of course, there are a lot of debris. Dead satellites are still rotating around the Earth. Some of these are geostationary. Some of these are polar. And the classifications is there could be meteorological, there could be GPS, there could be military-based satellites. So satellite data is again like a volcano spewing the lava. The satellite keeps spewing the data all around. What's one thing about polar satellites? You all know, but I'm going to tell you. The Earth is rotating. The polar satellite is also rotating. So by the time the polar satellite finishes, the Earth has moved, so it doesn't see the same part. Okay? So it tries to sample different parts of the Earth along certain tracks. In fact, I collaborated with a student at the Indian Institute of Science. There was a pressure. The ministry said, we have given you satellite. What did you use the satellite data for? That's right. I think they have the right to ask that question. We scientists asked the government to spend $500 million to give satellite radars and other things. They spent taxpayers' money. How did you use taxpayers' money? What can you tell the taxpayers? What are they getting back for that investment? So this satellite data was about the aerosol distribution. There were in situ measurements about 10 to 12 stations in northern parts of India. So they wanted to be able to merge the in situ measurements, which are much more accurate, with the satellite data, which is plenty, but not, there's too much uncertainty in satellite data. So we were to create a mosaic of these two, combining these two, and that was one of the PhD thesis that came out a couple of years ago. So he particularly used the polar satellite data, especially with respect to aerosol distribution across the continent of India. So what are the problems in data analytics? Data science, don't be fooled. They are all similar. Okay? They will call visualization. They will solve visual analytics. Is there a difference? No. Text data analysis, text analytics. I'm trying to tell you that there are lots of ways of expressing similar ideas, and they are similar. So, what are the basic problems in data analytics, which is data science? One is classification. I had 3 PhD students work on classifications of meteorological data. I have a couple of 3 papers. I will discuss this. Tomorrow I'm going to start the classification problem, clustering problem. Once I do the clustering algorithms, I will give you the papers that relate to the applications of those. So clustering classifications. So what is one problem we worked on? They did an experiment at NSA. How many of you know NSA? NSA is the major research organization stationed in Washington, D.C. They are the backbone of Meteorological Prediction Center in Washington, D.C. So NSA is primarily for research that feeds into the online forecasting. So the NSA, they wanted to do a summer experiment. They have picked about 12 different models. Basically, there are only 3 or 4 models, but they changed the physics. They wanted to create an ensemble of behavior from these 12 different versions, which are created out of 3 fundamental models with varying physics, varying initial conditions, varying parameterizations, and other things. They wanted to analyze what did the output mean to them. So one of my students from Saudi Arabia was completing his general exam, the qualifying exam in computer science, and my colleague in the meteorology department suggested this problem. He worked on his PhD, and I will give you a copy of the paper to him. So the goal was to find out, do models agree? Do they differ? If they agreed initially, do they continue to agree? If they differ initially, they continue to agree later. They wanted to understand the predictive power and the differences between the various types of models. I'll show you the results a little later when we talk about that. That's classification clustering. Processing of queries in large database. I already talked to you. Fingerprint. Okay. Facial recognition. CBI, FBI. Yeah, CBI, FBI. All the detective organizations. Feature extraction, dimensionality reduction. I already talked about it last class. So I have a set of objects. I want to be able to classify the set of objects. Remember? So that's called features. I may have a million features, but not all features may be useful. So which features are more important than others? Just like in modeling, we want to ask ourselves the question. A model cannot capture all the properties of Mother Nature. I'm interested in capturing only the large-scale features. Everybody remember it? That's what models are supposed to capture. So, so in feature extraction, I may have extracted too many features, but not every feature is important. If I want to use all the features, it may take more time. So I want to be able to do a pre-processing that can assess the importance of various features for the problem at hand. And that comes from what's called dimensionality reduction. Please understand, big data may be very highly correlated. Big data implies large volumes of computation. So why to spend money when your data doesn't tell? More is not merrier. More correlated data is not merrier. So I would like to be able to reduce and find out a subset of key features. That's called dimensional reduction. Look at this now. We cried that we didn't have too much data. When we have too much data, now we say it's correlated, I want to data reduction. That's right. That's right. Okay? That's right. So there are lots of algorithms in data science that relates to dimensionality reduction. We will talk about that. The last one, least squares problems arise in various guises in various applications. As I told you, every neural network essentially implements some aspects of nonlinear least squares. Okay? So, deep neural networks, there are a number of stages, there's a number of variables of large. So you get a very large least square problem. To be able to solve the problem, it's not that I don't know how to solve, but that problem to be able to solve exactly may take a large amount of time. So what's the question? Can I get the major features of the solution quickly by approximating the solution? Think about it now. Approximation is a various tool. There are very few problems we know how to solve exactly. You all know that. I don't know how to tell you that, especially in meteorology. Without approximation, we don't have jobs. Approximation is a way of life. So when the problem becomes very big, not necessarily difficult, we would like to be able to solve those least square problems approximately to get a good feel for the solution, to see whether I have captured all the major important features. But I will to the complexity a little later. I don't want to bore you at this time. Now, how many of you know the notion of computational complexity? Raise your hand, please. I'd like to know. Thank you. Because many people did not raise the hand, I'm going to give you a quick feel for the complexity. Many times what we say, oh, I have a problem, I have an algorithm, I solved it, it took 2 days, that's all right. But how do you measure the complexity? And that's very important for the following reason. Why? I have a problem of a given size. I have a computer with a given power. I'm interested in forecasting. The forecast has to be developed every 12 hours, every 24 hours. If you don't produce forecast, you don't have a job. So for a 24-hour forecast, you have to do data assimilation. So you have to wait for collection of data. The model is already there. You have to wait for assimilating the data into the model. You get the assimilated model. You run the model forward in time for 2, 3, 4 days. And then you announce that forecast to the public for consumption through radios and TVs and every other channel. The next day comes. Just because you made a 3-day forecast, can you take rest today? Hell no. You will not have a job. The next day, new data comes in. You repeat the show. So within a 24-hour period, if your job is to be able to create 2-day, 3-day forecast, how much time do you have to assimilate? You don't have 24 hours. The data doesn't come to you until after 6 p.m. Tomorrow morning, 4 o'clock, your products have to be ready. So how many hours you have? 6 hours, 5 hours. So what's the question we need to ask? Within 5 hours on this given machine, what is the largest problem I can afford to solve? Do you see that, please? While doing PhD work, we don't worry about that. That's all right. That's what PhDs are for. But when you are interested in trying to make a forecast. During Olympics, they have to make 3-hour forecast. Especially during Winter Olympics. Winter Olympics depends on ice. There'll be ice this morning so that I can have skating competition. So in some cases, you may need a 3-hour forecast, 6-hour forecast, daily forecast over a period of 24 hours. So where the computational complexity comes into the picture, given the time period that you are allotted for being able to do the data assimilation, the size of, so you have to decide the size of the data. You have to decide the size of the model in terms of the bit size. And you have to worry about that computing power on this computer within 6 hours. Looking at the largest data set and the largest bit size, I can afford to handle. So how do we computer scientists deal with this? That is done by what is called the complexity analysis, and that's what I'm going to talk about it. It's going to be 11 o'clock very soon. Our first lecture is from 10 to 11. I want to keep the train on time. 10 means 10. 11:30 means 11:30. I won't hold you much longer. Please cooperate. And so the only 2 minutes, I won't start it. I will probably start it after in one of the lectures. You will address that question. But in the meantime, given the time is short before the tea break, are there any questions? I would like to encourage questions. You can stop in the middle. You don't have to wait for me to ask you last questions. Hello, those of you who are online. Hello. I'm not able to hear. I hope so. I know somebody's talking.
They can't check the chart.
Or target. Is that somebody doing it?
Yeah, so there's no question on it.
Oh, there's no question. Good. Thank you, sir. Please keep track and let us know when there is a question. Anybody? Any questions?
What are the
I'm sure.
So when we see big data analysis,
Ah.
as much we know the data source and means like how large the data is important and how the resolution, as you have mentioned, many fields have the many large size of data it's produced.
Mhm.
So what is the role, means like very peculiarly we have to think about in the big data analysis in what you have listed in many factors.
That's right, that's right, that's right. Please understand, I can make it as big as I want. Hope you got the idea now, right? Especially in meteorological problem. I can have one data for every square mile. That's one of the final resolutions. Can you go for that? That depends on other things. How large the data set is going to be, how large a computer you have, how large a storage you are going to have. Let me also ask you this question now. If you have a lot, in almost all the computer analysis, we assume the program and the data reside in the fast RAM memory. How many have heard me? If the data is too large to be held in the RAM memory, you have to put it in the secondary storage. Then you have to hold the computation until my processor can go see the data. That's going to be much delayed. So to answer your question, there are two factors to this. First thing, I want you to appreciate, I can make the data as large as I want. So who makes it big? You, me. How big can you afford? That depends on other parameters. Do you have a good algorithm? Do you have a fastest computer? Even the fastest computer money can buy, the memory is limited. So what is the largest size problem I can store in the memory at this time? Above all, what is the amount of time I have to solve the problem before the deadline comes into play? Okay? So I want you to appreciate your freedom on one hand, your restrictions on the other hand. You have freedom to create the data as large as you want, but your restriction coming from other aspects that determine how fast you can compute. Ultimately, our job is to let the public know what the weather is going to be. And that cycle is 24-hour cycle. You got it?
Yes.
So I want you to be aware of both sides of the argument. Any other question? If not, I believe the key is waiting for us. We shall meet at 11:30 sharp. Thank you. Would you know how to switch it on? You know, I didn't know how. Where is the check? Oh, right. So the red light means it's off. Yes. You look very good. So can you go to the next?
Hey. I'm also from Central Water Power Association. It's a different instrument. We are directly working together in one it. Actually, I'm electrically engaged. I'm from Guinea Engineering College.
Now,
Selvam.
the Guinea is not a better.
Samadhanam.
My wife is from Bangladesh. She good. Sata, a man from Samadhanavaram. Okay.
As I go Pune, sir, I've been here for the last 25 years. I have worked with Central Water Commission. So we took part in the flood warning, disaster management.
Did you come yesterday?
I got a message from Mr. Manmeet Singh. So we are working together on some postal.
She was staying in
Selvam.
Could you open that slide, mathematics of data? You can pause this.
Okay.
Kaadu was working in circus.
The file, I thought he had a file, the person who came earlier, the small pallet. Yeah.
So every 3 years. I attended your lecture. So I just wanted to know what is the next lecture?
I'm going to talk about mathematics of big data.
Okay.
In other words, some of the challenges in big data. You probably do not often get to hear, so I wanted to be able to broaden the base. These are useful to you?
Yeah. Yeah.
You up here?
Yeah.
Very nice. Let's have a cake.
Yeah, please text. Actually, last time I missed your talk, so yeah, this time I thought I'll attend yours.
So last time
Last time I visited Data Assimilation.
Good, I'm glad you're here. Once I'll let you, there's mathematical data analysis.
We came Saturday night.
The mathematics of big data.
Sunday on the.
Yeah, the first 24 hours, please do that.
The Shomeshwar
That's it.
in the morning and from. Thank
Thank you, sir. Awesome. Thank you.
Balaji Mandir. அதுக்கப்புறம் நேற்றுக்கு ரீடிங் போயிருக்கோம். இன்னைக்கு we don't have practical class. நாளைக்கு நாளைக்கு யார் போறா? யார் வீட்டுக்கு போறாங்க?
Okay. Continuous time. The beat has both discontinuous and discontinuous time. Yeah, that happens. The real time is continuous, right? The clock is running. So the pressure is varying continuously. Your heartbeat is continuously doing. I know, that's why we discrete. But then a differential equation, when you say x dot, the time rate of change, instantaneous time rate of change. Not every data. So let's suppose we have a differential equation that says x dot is equal to ax. The x change is continuously. So what is the solution? X t e to the power of a t x naught. E to the power of a t is a continuous function. Then what you do? You just try to decide. So most of the models of interest in geophysical sciences arise from conservation laws. Mass is conserved, energy is conserved, momentum is conserved, entropy is conserved. Conserve every point of time. So you formulate your conservation laws in continuous time. All the models are derived from the conservation laws. So most of the physical models are expressed in continuous time, but the model equation becomes nonlinear. I can't solve it. So discretization is a substitute that helps our ignorance not to be able to solve nonlinear systems. So it is not part of the process. It is because of our inability to solve. Got it? Yeah. Got it. Yeah, so after you assimilate data, you make a forecast. Then that forecast is a perfect no, that's a forecast error. So what is it you now need to think about? That forecast error doesn't grow in time. So if the error doubling time is 2 days, then you can only believe 1 day forecast. If the error doubling time is 5 days, you can believe 3 day forecast. No. Data assimilation doesn't do anything. You give me the data. You give me the model. The data assimilator essentially combines the model with the data. He doesn't touch anything. It has no relation with the data. It has no. Okay. At the time of data assimilation, you don't talk about the properties of data. The data collector, before he or she gives it to the data assimilator, they have to clean it up. At the time of data assimilation, I assume it is ready to serve. I can't do everything, right? Data assimilator cannot do everything. So the model guy determines the model. The discretization guy discretizes it. The programming guys develop the model code. The data guys look at the satellite radar, its measurements, and everything else. Then they create a mosaic of data that is ready for assimilation. So the data department, they are responsible for giving me the right data. You can't do everything yourself. So you have to divide and conquer. You have to divide your job. Okay? And the data assimilator assimilates it, and he makes the prediction. And there's somebody to be able to evaluate the quality of data assimilation by measuring the forecast errors. My forecast can be accurate up to 4 days, upgraded in 5 days, and so on. Got it? You work in IITM. Which page? What are you working on? Who is your advisor? Okay. Which year are you in? Oh, just which part of the country are you from? Nice. You don't do VT dimension. Every network has an inherent VT dimension. So you need to compute the VT dimension of a given structure. It is not inbuilt anywhere. Given a structure, you have to compute the VT dimension. There are mathematical methods. That's what the references I talked to. Right? Go ahead. One of the book I told you, the Vidyasagar's book. That generalization, that is a very nice account of VC dimension. And you can do VC dimension and Wikipedia, that's very good information. So there are a lot of information about VC dimension. I'm glad you are talking about it. It's very important for you to be able to understand the notion, the concept, and how to compute VC dimension and build special courses just to build it. Because computing VC dimension is not easy. No, it's not optimization. It helps you to be able to quantify the performance of the yes, how can you guarantee the performance? Okay. Okay, what I don't think I have a course, but I can write it down.
Madras, he's a second year mechanical student. So I am married, working in Somalia.
Sure.
So I'm just coordinating. So asking knowledge, like I am.
Sure.
It's a BU.
OU that University of and my local number. My local. I have an Indian local number. I don't.
You can call me so that
Yes, I'm a very good friend of mine.
oh, even if it was next and was a scientist in my institutes, then we moved
That's it. Tomorrow evening. I know.
So 98 he was in
He got excited. He got excited. No, don't look at this.
This is my investment. My SIM card is an Indian SIM card. So this will be actually. But email is always the same. Thank It's good that. Just to remind people. All right. We still have few more minutes. Oh, Mr. Singh, is there a way to know how many are in the YouTube? Just want to find out.
So there are
Is there a way for you to poll them to see where they are? Or direction of the composition? Their page is for their staff.
I can ask the question. I asked them the same question. So there are 10 people who are watching, and nobody has asked them questions. Just ask them.
Is there a way for you to finish broadcast?
Yeah, I just
Please
asked.
identify who you are, where are you from, and what's your interest.
Sure.
Maths, PhD, masters, some information about each other, and their email IDs as well. We still have 3 more minutes. We wait. The computer says 11:32. My watch says 11:27. Which one is right? We'll take the average. Okay, so we'll go with this one. Okay, give us a couple of more minutes.
Everyone is here.
Okay.
I think you can start. Everyone is here. And
You can start everyone's sleeping. The flights are not supposed to start early. You can be late, but not early. Someone came to me asking that they want to hear about how data assimilation is an inverse problem. Who is that person? Raise your hand. Yeah, good. So that's a good question to ask. So yesterday we talked about answering that inverse problems. And our friend asked me to see if I can elaborate on that. So what's my request to all of you? If you think there's a particular topic that you would like to have me talk, please talk to Partha or Vinay. And you need to do it very quickly so that then we can try to see the only 3 more days I can accommodate the question. So we have to put a deadline. I know you all know there is a proverb, right? But for the deadline, nothing gets done. Do you know the proverb? Come on, guys. Please put it down in your study. But for the deadline, nothing gets done. So what is the deadline? Before the day is over today. So before the day is over today, if you can send an email to Dr. Vinu with a copy to Partha, telling what kind of topics you folks want to see, then they can share it with me tomorrow, and we can plan on Thursday and on Friday, depending on the length and breadth of the request, to be able to accommodate as many. I don't want to pick and choose, so the request will be taken in the order in which it is received. So if you want to have something done, do it, please. Okay. Thanks. With that, let me start. It's 11:30. I'm going to give you an idea of the big data. What is that? Sometimes we get entrenched in our own work. I've been there. Yes, I want to publish a paper. I want to get my PhD. I want to get my master's. So we try to get well focused, and that's the right thing. There's nothing wrong. But I would like to provide you a bird's eye view of related things which you may not have a chance to hear. So here, I want to tell you that is a very nice book which was published very recently. I like this book. It's the book on mathematical foundations of big data analysis. There is something in common with the title I have, but the topic I'm going to talk about is not dealt in this book. There are other books that deal with it. So I'm going to pass this book around. You may want to take a copy if you want to buy yourself, or you can ask the library to buy. That's the best way to do it. So please circulate as you go by. So I'm going to talk about mathematics of big data analysis, an introduction. Hope it won't be a distraction from the lectures. We already talked about the abundance of data. I don't want to repeat this. There's a shift from sparse to dense. Now, I also mentioned this last class. There are only 4 ways of organizing data. The data is in the form of a time series, or it's a spatial data, as a spatio-temporal data, or data in the matrix form. We talked at great length about creating data in the matrix form in the last lecture. Face recognition, fingerprint recognition, text analysis. Okay. That's right. So these are primarily the 4 ways in which data can be organized. So the entire data science deals with one or more of these data organizations from a data perspective. Okay. In this talk, I'm going to talk primarily about data available in the matrix form. Time series. How many different time series I have? How many companies are there in India? Every company has a stock. How many products agriculturally we produce? How many industrial products India produces across the whole country, state-wise? Oh, can you all hear me? Even without it? But anyway, I'll put it. Thank you. I tried to. I didn't realize it. Thank you, sir. Is it on? Yes. Thank you. So, if you look at the number of time series of agricultural products, the number of time series of bank stocks, industrial stocks. If you think of time series of exchange rate between Indian rupee and every foreign currency. You can keep adding. Then you have time series of meteorological data. So time series, there are 10 of them. So the area of time series is very big. So big data arise in the form of time series in various sectors. Meteorological, industrial, agricultural, economic, foreign exchange rate, stocks of companies. Hope you got the idea now. So if I'm working for Planning Commission for India, if you're working for the State Finance Corporation, if I'm interested in economic analysis of the well-being of the state, I have to deal with tens of thousands of time series. So what they do is big data analysis in the form of time series. Spatial data analysis, I don't have to tell you that. Spatial temporal data analysis, I don't have to tell you that. Most of the data in geophysical sciences, they are very naturally spatial. Now, I'm going to talk about some of the big data analysis within the context of matrix. I already talked about matrix data. I also gave you a meteorological example of classification. You remember the one that I told you before the tea break? That I have 25 models. Each model has different kind of parameterizations. Each model is starting from various initial conditions. I'm running all the models forward in time. I would like to be able to understand what the model says. This is called multi-model ensemble analysis. You all know ensemble methods, right? Everybody. Kalman filtering, ensemble methodology. Here, in Kalman filtering, we have a single model. We create an ensemble of initial conditions. We look at the ensemble of all the forecasts coming from different initial conditions arising from the same model. The example I just finished talking about is multi-model ensembles. I also mentioned it yesterday that the Hurricane Forecast Center in Miami, Florida, in the United States, they have about a dozen different models produced by different research groups. Who is to say which model is better? Run all of the models forward in time. So given a hurricane, get the data, run the model forward, make the data simulation, run the model forward in time, look at the forecast, and then humans try to decide to be able to generate a forecast for public consumption. Public need only one information, even with that they are confused. So we don't want to confuse the public more than necessary. But we, as scientists, have to take the responsibility. How do I generate one product for public consumption? When in fact, there are 12 models looking at the picture, there are 5 experts trying to interpret the 12 models to be able to create one that is useful. So in that case, I have to be concerned with how the models behave with respect to each other. That's a classification problem. Okay. So the matrix kind of data naturally arises in many walks of life, especially in geosciences as well. So the data is given in the form of a matrix. Earlier, I had used M as the number of rows. Here I'm changing it to D. Why not? The row smells the same. So I have a matrix D by M. D is the number of rows, the N is the number of columns. Each column is a vector of size D. The N columns represent N points. You can think of the data as N points in the D-dimensional space. D is very large. Okay? In the case of facial recognition, D was about 500,000. The number of people whose faces I have, maybe 2,000. So 2,000 faces in a 500,000 dimensional space. That's the kind of problem that we are talking about. So this data can be large because the N, the number of data items, can be large. This data can be large because the size of each column, the number of features that I use to represent the object D, can be large. Both of them be large. So similar measures apply to other data organizations, spatial temporal. Is it regional data? Is it global data? Is it annual data? Is it monthly data? Is it daily data? I already talked about time series. So in different organizations, data can become big in different ways. Number of time series, global versus regional. Time in terms of hours, days, seasons, decades, centuries, different time scales. Okay? That's fine. So, but I'm going to concentrate largely on the matrix level data. Who are the people who are dealing with big data? Statisticians have been dealing with big data for a long time. That's what statistics is all about. Almost all the theory in theoretical or mathematical statistics are asymptotic in nature. Asymptotic in what? N, the number, and then goes to infinity. So in classical statistics, there are a number of asymptotic results obtained by fixing D, by varying N, and letting N goes to infinity as the number of samples increases the bound, where D over N goes to 0. I'm considering the properties of vectors of size D fixed, but there are a large number of vectors, the number of vectors go to infinity. This asymptotic theory provides the basis for base estimation theory. I argued in the last class that estimation theory is fundamental. Many aspects of data assimilation deals with estimation. You cannot do data assimilation without a decent understanding of estimation theory from basic statistics. That's what estimation theory. That's the role played by estimation theory. So what are the bases for this estimation theory? There are tactical statisticians, there are theoretical statisticians. The theoretical statisticians provide the mathematical basis that the practical statisticians use. They stand on the shoulders of the theoretical results that the mathematical statisticians generate. So what's the typical result from mathematical statistics? Of large numbers. So what does it say? I'll give you a quick example. I have a black box. The black box is supposed to generate random numbers from normal distribution. I don't know the mean, I don't know the variance. My job is to be able to estimate the mean and the variance. Please understand, if you are going to do data assimilation, this is the first problem you need to learn to solve. Because data assimilation is estimation. What is the song you learn when you learn piano? Twinkle, twinkle, little star. How many grandparents say, oh gosh, my child is only 2 years old, she can play Twinkle, little star on my piano. No matter where you are, the first lesson in piano all over the world is Twinkle, twinkle, little star. So what is the twinkle, twinkle, little star for the estimation problem? This is it. You can't become a musician without learning Twinkle, twinkle, little star. You cannot start understanding data assimilation without probably solving simple problems of this type. So I want to learn. Do you think of this as so what is AI? AI is learning about something I don't know. I'm learning ride a bike. I'm learning to cook. I'm learning to play cricket. I'm learning to swim. Don't you say that? So if learning something we don't know is fundamental aspects of human endeavor, learning is there in many places. So this estimation problem, if I'm learning the unknown, can you call it learning algorithm? Yeah. But statistician didn't call it learning. Within AI, we call it learning. Why am I mentioning this? Not to criticize anything, but to tell you what we call in AI was called by some other name way back in time. Okay? Knowing the unknown is learning. Trying to compute the unknown mean and variance. There's a statistical algorithm In some sense, you can think of it as a learning algorithm. We don't give too much importance to it as a learning algorithm because we do this routinely. Okay, now how do we estimate the mean? M is the unknown mean. The mean is estimated as a sample average. So I'm able to draw n samples independently from the identical distribution because the black box is the same. I'm going to independently have n samples. So x1 to xn are n samples. It can be shown that the numerical average of n samples is an unbiased estimate of the mean. Unbiased. In data assimilation, you all need to know this. Many of you may say, well, there's a bias in the estimate, right? So estimate has to be unbiased. The properties of one of the properties of estimate must be unbiased. Where does it come from? It comes from basic statistics. So what does log logical say? As the n becomes large, my estimate x bar n. Now x bar n is the average of n random variables. A function of a random variable is a random. So x bar n is an estimate that is random. So xi is kind of distribution. What's the original distribution? The normal with unknown mean and the variance. That each of the xi's being random induces a probability distribution over x bar n. The distribution of x bar n is called sampling distribution. Obvious? What is the way to think of it now? I have given a coin. I don't know whether it falls tail or head. I'm going to toss it 50 times. Register how many times head, how many times tail, and do it second time. Do it third time. Do it 10th time. Each time you repeat the experiment, do you get the same number of heads? Come on, guys. You shouldn't. You will not. So the number of heads divided by the total number of tosses is an estimate of the probability with which it falls head. So if I repeat the experiment 10 times, I have 10 different estimates. And that's a distribution. That's a sample distribution. In fact, there is a joke. I already told a joke, so we have to laugh at the end of it. So there is a multiple choice exam. The guy tossed dice and took the exam. The exam was over, and then he started redoing the tossing. The examiner went and asked him, "What am I trying to do?" "I'm trying to check." How many of you got it? Come on, guys. That tells you the story. That tells you the story. So this random variable has a distribution. It is clustered around the unknown mean. The probability that this one will differ from the true mean by an amount epsilon, which is small, that goes to 0 and then goes to infinity. That's called law of large numbers. How many of you have seen this? Come on, guys. Where did you go to school? Did you take a course in probability theory? Did you take a course in statistics? Come on, guys. Truly, how many of you know this, but you have forgotten? You should know this, but you have forgotten. So what does this tell you? As you increase the number of samples, your estimate becomes better and better and better. That's a large sample theory. So a practical statistician coming and asking, "Hey, I can't do the experiment infinitely many times. What do I do?" Then the theory person tells you, in order to be able to estimate the unknown mean from the samples, you must have at least 50 samples. You must have at least 100 samples. Let me give you an idea now. They all take polls, right? Do they? Who is going? They want, before the election, they want to predict who will win. We can't wait for the votes to be counted. So as soon as people come out to the voting booth, whom did you vote? Whom did you vote? I'm not going to tell you. They tell you something. Are they bluffing? I don't know. How many of you tell whom you really voted? If you voted for a not too so popular person, you don't want to tell outside. But as a statistician, I'm going to collect the data, I have to estimate. So from my sample of 1,200 people on the street who already voted, it looks like so-and-so is getting majority vote. Are with me? Why 1,200? Statisticians have found out what is the minimal number of samples you must have in order to be able to make a prediction with some reasonably good accuracy. And where do these results come from? Law of large numbers. So practical statistics stands on the shoulders of theoretical statistics, and theoretical statistics provides you results that truly depends on law of large numbers. These are fundamental theorems. It is these theorems give us the right to do what we do. So I want you to be able to. So when I first asked a question, not many raised their hand. When I said, how many of you knew but not remember, then most of the people raised their hand. You cannot have had a master's degree without doing this in some course in probability and statistics. And why is this important? If you think you are doing data assimilation, you are doing estimation. This is where the estimation theory starts. Don't forget the roots. That. So this is called asymptotic consistency. It's also related to what's called measure concentration. I will come to that in a minute. What is an associated theorem? X bar m is the estimate. M is the unknown mean. I'm trying to normalize it by the variance, by the standard deviation of that. And what does law of central limit theorem tells you? That variable, which is this variable is a random variable, converges to the standard normal distribution as the number of sample goes to infinity. So two large numbers, both of them are asymptotic. Both of them rest on the fact that n goes to infinity, big data. Big in what sense? Big in the central number of samples. All of you? Come on, guys. So this has been done in statistics for a long time. So when we talk about big data today, I cannot repeat this. They will say, hey, get some life. So in what sense big data are going to become big? D is large. Here I said D is fixed. Not only D is large, the ratio over D over n can go to infinity, D can go to infinity. The ratio can go to 0. The ratio can blow to infinity. The ratio can tend to a constant. Ultimately, there are three possibilities for the ratio, D over n. D over n can explode, D over n can implode, D over n can tend to a constant. When D over n tend to a constant means what? D and n are comparable. When D over n goes to infinity means what? D grows faster than n. When D over n goes to 0 means what? N grows faster than D. When D and n grow together at similar rate, D over n can be a constant. At the new part of the statistics that big data analysis gives us. So what does this mean? Centered scaled estimate converges and distribution to standard normal Gaussian. So now we've got high dimensional data. So big here refers to high dimension. D is large. I already talked about who makes D large in the previous talk. It is you, it is I. It depends on the resolution I need. So there are several problems of interest in here. So we are particularly interested in the ratio D over n is equal to alpha equal to 0. All of you met? So what are the implications? Many of the known results in classical statistics when applied to D over n is equal to alpha gives only suboptimal results. So I need to be able to understand the analysis of high data to make it optimal. To address this challenge, a new specialty is emerging. These are the two books which I have referred to in the last lecture yesterday morning. One is the High Dimensional Statistics and Non-Asymptotic Point of View by Cambridge University Press, published in 2019. Another is the one 2020, the High Dimensional Probability Introduction with Application to Data Science. Both are very highly mathematical, but they are the cutting edge of research. in mathematical statistics. That's absolutely relevant to big data analysis. All of you, please. In other words, big data, I know data science, many of you, AI, many of you are already talking about. So when you talk about AI, what do you immediately think of? Neural networks, DNN, CNN, so on and so forth. But that's not the only thing. There are lots of other aspects of it. Again, that's where I'm coming from. So I'm now talking about the big comes from high dimensional data. There's a concept called curse of dimensionality. We all know that. In fact, it was coined by Richard Bellman, a mathematician. He coined that word when he developed the theory of dynamic programming in the year 1952. Many of you may know there is a branch of science within AI called reinforcement learning based on Markov decision processes. That's an example of a dynamic programming. And what's the problem in dynamic programming? In a d-dimensional space, it requires 2 to the power of d computations. 2 to the power of d, as d goes, it explodes. So the amount of work that you have to do grows with the dimension exponentially. That's a mathematical challenge. All of you? Okay. So the concept of curse of dimensionality has been around for a long time. Our aim is to be able to harness this complexity. Now I'm going to present a lot of results that are counterintuitive in high dimensional space. Let me, instead of talking about this now, let me go with examples now. So let's consider a cube. V subscript d, volume of a cube in d dimension of side A. The subscript refers to cube, d is the dimension, A is the side. Many of you may think, gee, I'm interested in radar meteorology, why am I talking about this? Right? Come on, guys. Yes. But it's very easy to think of only one problem, but you need to come out of your silos to think about what big data, if you're interested in big data analysis, what are the various things you need to be aware of. That's what I'm coming to talk about. So the volume of the cube we can compute. Now I'm going to tell you some important things. If you consider your cube of length, cube of side 1 in 2 dimensions, that's a square. AB is the diagonal. The length of AB is 2 times OA. Because it is unit side, this half-half by Pythagorean theorem, OA is 1/2 square plus 1/2 square root. So the length of AB is 2 times 1/2 square plus 1/2 square. So the length of AB is square root of 2. Everybody? Now, what is the length of the diagonal in a cube of side 1 in D dimension? If I proceed analogously, which is the right way to do it, the length of AB is 2 times AO. I want you to be able to imagine a cube in D dimension. Instead of 2 sum, I have D summation square root, and that becomes square root of D. Think about it for a moment now. I have a cube of size 1 fixed. The size, the length of the side is fixed in all D. And the length of the diagonal increases as a square root of D. Do you see that, please? How many of you see that? The cube deforms. It stretches. The diagonal increases as square root of D, while the side of the cube remains consistent. They remain constant. It's not constrained. It's a constant as D increases. Now, what is the impact of this? This is a very strange phenomenon. I'm now going to talk about the impact of this. I'm sorry. So another property is that if I double the size of the cube, the volume of the cube grows up by 2 to the power of D. We all know that too. So with these two facts, I'm now going to talk about sphere, and then I'm going to talk about some strange phenomena that happens. So V subscript S dr is the volume of a sphere of radius r in d-dimensional space. You can think of, a sphere in 1D is an interval. A sphere in 2D is a circle. The real sphere 3D, 4D, 10D, any D. The volume of a sphere is given by this formula 6, pi to the power d by 2, r to the power d divided by gamma of d by 2 plus 1. You all know probably gamma function. Gamma functions are extensions of factorial. So that's what equation 7 says, and gamma half is square root of pi. Anybody who has done a little bit of probability theory should have seen this. So now I'm going to compute the volume of a sphere. Look at that. A volume of a sphere in 3 dimensions is 4.1867 of radius 1. A volume of a sphere in 3 dimensions of radius 1 is 4.1867. The volume of a same sphere of radius 1 in 10 dimensions is 0.0248. In fact, it can be shown that the volume of a sphere goes to 0 while I keep the radius constant at 1, but the volume, but the dimension d increases. What does it mean? It's a strange phenomenon. This is called creation of empty space in high dimension. The counterintuitive facts about geometry. Are you convinced from these two examples? That's right. Yeah. Sphere in 10 dimension has a very little volume, but a sphere in 3 dimension has a large volume. So if you plot the volume versus d, you can see that the volume goes to 0. Volume goes to 0 means what? Emptiness. So in high dimension, empty spaces create. And that brings up the following question. What must be the radius of a sphere in d dimension in order that the net volume of the sphere is kept constant at 1? Earlier I kept the radius constant, now I want to keep the volume constant. I want to ask a question. Because the volume goes to 0 as d goes to 0, in order to keep some non-zero volume, the radius has to increase. How fast I should increase the radius in order to entrap your volume, unit volume in the sphere in d dimension? It can be shown that by using well-known approximations, the radius must increase of the order of square root of d. What is d? D is the dimension of the space. Are you there? So how many of you this is new? All right. I want you to have an aha. This is the geometric facts. So we talk about big data. Big data means high dimensional data. We need to understand basic aspects of high dimensional data and the basic idiosyncrasies of properties of geometric objects in high dimensional data. So empty space syndrome happens very naturally. Now I'm going to consider a cube and a sphere, and this has a lot of implications for doing simulations. I'm going to get there in a minute. So consider a cube of side 1 in d dimension embedded within a sphere of radius 1. So this is the 2D representation. The radius is 1. That's a sphere. This is the cube of side 1, totally inscribed. We have seen that the AB varies as d grows. AB varies as square root of d. How many of you remember that from the previous slide? That's right. So for d less than 4, AB is less than 2, the square is inside the sphere. When d is 4, AB is equal to 2. AB becomes the diameter. For d greater than 4, AB is greater than 2. What is the diameter of the sphere? 2. That means the diagonals of the cube pierces through the sphere. Have you seen the caricature of the COVID virus? Come on, guys, you have not seen that? Everybody has seen that? That's right. So you can create a caricature of the COVID virus. So how many diagonals does the cube have? A d-dimensional cube has 2 to the power of d vertices. You need a pair of vertices per diagonal. So that is 2 to the power of d minus 1 diagonals that pierce through the cube. And this is a strange fact that comes from geometry. It looks like a COVID virus. I'm now going to talk about another thing. Suppose I have 2 spheres, one of a larger radius and a smaller radius. There's an annulus region. So I have the difference in volume. The volume of a larger sphere minus the volume of a smaller sphere refers to the volume that is trapped in the annulus divided by the volume of the larger sphere. That is given by this formula. That is given by this formula. Little r is greater than capital R. Little r over capital R is less than 1. That goes to 0. So what does it mean? The entire volume of a sphere is not to be found inside. It is trapped in the periphery. How many of you with me? Come on, guys. And this has a lot of implications in simulations. And we saw yesterday, data science is different from computer science. Data science depends on probability theory, statistics, simulation. So suppose I want to simulate. I want to be able to draw random variables from a sphere of radius 1 in 100 dimension. Suppose you have a problem that I want to be able to generate. You know how to generate random numbers from a square. You know how to generate random numbers from a 2-dimensional circle. Suppose I want to be able to generate random numbers from a unit sphere of 100 dimension. There's no probability in the center. All the probabilities are around the circle. So the concept of uniform distribution go by the wayside. And how many of you are interested in simulation in your work? Many of the things we do is simulation. To be able to simulate, I want to be able to generate random numbers. I want to be able to generate random numbers from various distributions. Simulate numbers from a cube, simulate numbers in a sphere. So the notion of being able to simulate, which is a fundamental tenet in data science applications, you have to call the question, namely, where is the mass? Where is it located? If there is no mass, I can't start. All of you with me? You all have an aha here? Okay, I want to tell you this. I have an aha theory. I believe in aha theory. Sometimes when you talk to people, how is it? They'll say, okay, fine. It's a typical answer in India. Don't mistake me. I'm an Indian. I got my PhD from India. Are you with me? So I'm not talking about anybody but myself too. Okay. Have you seen tennis players? When they make a point, what do? Enjoy the moment. When you learn something, don't say fine, don't say okay, say aha, say wow. Have you gone to concerts? Come on, guys. With a rock concert, nobody listens, everybody dances. It's a classical concert, nobody dances, but everybody says wow, 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 wow. How with me? So I don't want you to dance, I don't want to say wow, wow, but at least I want you to say within yourself, aha, I got it. Every time you learn something new, it's an aha moment. Are you with me? You need to learn to enjoy every aha moment in your life. Please celebrate. Is this an aha moment? Aha. That's right. Good. So what does it mean? The mass diffuses. That has lots of implications. So using a very simple geometry fact, we have come to recognize the challenges that this may pose in trying to do problems, large dimensional problems of interpreting data science. Okay. Now let me talk about a little more, just to give you different ideas. Earlier I talked about a square inside the sphere. Now I'm talking the converse. The sphere inside the square. The ratio of the volume of a sphere to that of a cube. I have the formula. You can see this goes as a factorial. This is exponential. Pi over 4 is greater than is less than 1. Pi is 2.411. So this fact goes to 0. This fact also increases the reciprocal. So this ratio goes to 0 in a hurry. All of it, man. So what does it mean? The volume of a sphere contained in a cube, the ratio goes to 0. When a ratio goes to 0, the denominator cannot go to 0, the numerator goes to 0. What does it mean? The volume inside the sphere migrates out of the sphere. Where does it go? It has to be contained within the square. And where they are to be found? They are to be found in the corners. And why is this important for a data scientist? Often we say, create 10,000 samples from a cube of size 1 in 50 dimensions. Create 10,000 samples from a cube of size 1 in 100-dimensional space. Are you with? But there's no bias on the center. So the samples will be biased toward the corners. If it is biased toward the corners, what does it mean? It is no more uniformly distributed. If the distribution is not uniform, you are screwed up. Your analysis is screwed up. All of it in place, you cannot make simple statistical conclusions easily. Charles, I'm not going to talk about solutions. We cannot find the solution until we understand the problem. So, counterintuitive ideas that arise from high-dimensional geometry, that is of generic interest in high-dimensional data analysis. That's the topic. That's the topic. You all have an aha here? Your silence is deafening. Come on, guy. Now, I'm going to talk about distances. Volume, measure, probability is a measure. If there's no volume, probability cannot be held. Now I'm going to talk about the behavior of distances in high-dimensional spaces. Some strange things do happen here as well. Suppose I have a unit square. I am generating 1001 random numbers from a 2-dimensional unit square. That I can do very easily. Why? It's a small dimension, no problem. Okay? Come on, guys. Is the problem clear? Now, out of the 1001 point, I'm going to randomly pick one point and keep it fixed. From that point, I'm going to compute the pairwise distance squared to every other point. There are thousands such pairs. There are thousands such distances. There are thousands squares of such distances. Each of the square of the distance is given by the formula, and they are no more than 2. The points are close, the distance will be close to 0. If the points are far apart, the distance will not be more than 2. So all the distances must lie in the interval 0 to 2, and they are randomly distributed. How many of you may? I want each of you to do this experiment this weekend. Just to be able to enrich your knowledge. So if you plot these distance square and compute the histogram, you will see the histogram is supported through the entire interval 0 to 2. There will be points close to 0, there will be points close to 2, there will be points everywhere else. That means the distribution of least square may not be uniform, but is everywhere. The support is through the whole space 0 to 2. That means the distribution the histogram is fully supported on the interval 0 to 2. How long does it take for you to write a program like this? 15 minutes? How long does it take for you to draw the histogram? 1 hour? Come on, guys. Please do this. I want you to enjoy doing all these things to be able to. Now let's do the same experiment in a 100-dimensional space. Something funny has to happen because I already argued. In a 100-dimensional space, the cube has volumes more close to the corners. There's not much left in the. So you are already ready for the game. So I'm going to generate 1001 point. Each point has 100 coordinates. Each coordinate is generated uniformly from 0 to 1. Everybody please? So 1001 point. Each point has 100 coordinates. Each of the coordinates are uniformly distributed in the interval 0 to 1. Pick one of the points at random. Compute 1000 pairwise distance square. That is given by the formula 10. It can be easily shown that this must lie in the interval 0 to 100. But a lot more is true. They are not going to be distributed 0 to 100. Something funny happens. Law of large numbers comes into play. You remember law of large numbers? What the law of large numbers says? If I add a bunch of identically distributed independent numbers, the averages, the sums, they all cluster around certain value. That's what the concentration of the law of large numbers is all about. So you thought you were doing a geometric fact, but because I generated the points randomly, the stochastic aspect of the analysis comes into play. So xi's and yi's are IID random variables. The squares are IID. The sum of squares, that's also IID. By law of large numbers, the distribution of d square is concentrated not in the entire envelope, but somewhere in the middle. So for small d, the distribution is spread out over 0 to d. For large d, they are concentrated. This is called concentration of distances. How does it mean? If the distances are going to be concentrated, what does it mean? We lose the ability to discriminate based on distances. And why is this important? In database search, there's a database, a query comes in. I want to be able to see who are all the elements in the database that are closest to that, and what do? I want to be able to compute the distance, the nearest neighbors. So any algorithm that is based on nearest neighbors in high dimension, the distance may lose its ability to discriminate. All of you? Because all the distances are very close to each other. All of you? That's right. These are applications for high dimension data. Now, one more. Before I go to another couple of other applications, there's a more interesting geosciences. We all know Gaussian distribution. Gaussian distribution is the bell-shaped curve. Gaussian distribution in one dimension, Gaussian distribution in d dimension. Everyone should know this formula 11. Formula 11 is the functional form of the Gaussian distribution with mean m, variance sigma in a d-dimensional space. How many of you are aware of this? Good. When sigma is a diagonal matrix where the diagonal elements are sigma squared, it becomes uncorrelated. And then I can write 11 as a product of individual Gaussian 12. I can, in this particular case, I can compute. So if I draw a random vector from this distribution, the random vector has a length. I want to be able to compute the expected value of the square of the length of the random vector from this distribution. All of you know what I'm talking about? X is a random vector. X is a vector, it has a length. If it has a length, I can square the length. Because X is random, the square of the norm is also random. Every random variable has a mean. So I'm trying to compute the mathematical expectation of the square of the norm of a random vector. How many of you are with me? Come on, guys. You need to know what I'm talking about, what animal I'm talking about. The animal I'm talking about is the square of the length of a randomly drawn random vector, its expectation. It can be shown that this is d times e of x on square. Why it is d times e of x on square? Because when my sigma is sigma square I, the components are independent. So using the concept of independence, I can essentially see that x. What is ex? E of x on square, that's the variance of xn, that is sigma square. So d times sigma square. That is because x has an IID, which I will read. So what does this mean? For large d, the random variable square of the length of the random vector of x is concentrated around its mean. So square root of d sigma square is the mean of that length. And sigma times square root of d is called the radius. Gaussian. It has, again, another great implication geometrically. I'm sorry, I apologize. This must be a Gaussian distribution. My program got screwed up. My program got screwed up by me and my student. Forgive me. This must be a nice curve. Now, what I'm talking about here. So I have a unit normal. This is 0. I want to be able to compute the probability measure that is in between +1 -1, -2 +2, -3 +3. So what is this? This is integral a to b px dx. In this case, I'm interested in -a to +a, where px is the normal distribution. So if a is +1 -1, that is 68% of the measure in here. There is 95% of the measure from 2 to -2, -2 to +2. There is 99.7 between -3 and +3. Think about this now. The distribution is from -infinity to +infinity, but 99.97% is just within -3 to +3. The probability with which large values can occur is very small. Nevertheless, it can occur. So these are concentrated around the mean. What is the tail? 1 minus is the tail. So the probability measure contained in the tail when a is 1, when a is 2, when a is 3. What does it mean? The tail has very little probability in the one-dimensional case as a increases. Tail means what? The probability with which large values can occur is very small in 1D. What is the analog of that in higher D? That's surprising. And that's what I'm going to present now. Yeah. So I'm now considering the standard normal, zero mean, unit variance. Everybody. Unit variance means the covariance matrix is I. I is identity matrix, whose diagonal ones are all 1. So I'm considering standard normal in RD. The probability that lies outside the sphere in one dimension is 0.3. This should be 4. 4353. In 5 dimension is 5494. In 100 dimension is 1. In 1 dimension, everything is around 0. As the dimension increases, this probability mass oozes out. It goes towards the tail. Where does it go? Does it go to infinity? No, it does not. We are going to talk about that in a minute, but I hope this is clear to all of you. This is called concentration of probability mass. Concentration of probability measure. So for large D, the tail has more information. For small d, the tail probability is very small. Are you all with me, please? How many of you have an aha here? How many of you know this for the first time? How many of you this is surprising? That's right. That's right. Where does it go? It cannot escape. Because mass must be conserved. It must go and hide itself from some place. Where does it hide? Do you remember we talked about sigma times square root of d as the radius of the Gaussian? As the radius of the Gaussian. So the probability that a standard normal contained within a small annulus. So think of a small annulus where the square of the norm is d. Are you with me? Come on, guys, the small annulus, the square of the norm of d. So what did that the law of large numbers now say? So this is random because x is random. What is the probability that it will be less than square root of d plus beta? What is the probability that it will be greater than square root of d minus beta? That means I'm going to sandwich the square of the length, the square of the length in a small strip of length 2 beta centered around square root of d. How many of you are able to visualize that? Come on, guys. Much like I visualized a small band from -1 to +1 centered around 0. Here, I'm going to concentrate around square root of d. Square root of d plus beta, square root of d minus beta. Within that small region, the probability mass is going to come and get concentrated. And how do I measure the amount of probability that is being trapped there, given by this inequality? The probability that the square of the length is contained in this small strip is greater than or equal to 1 minus 3 times e to the power of alpha beta square, where beta is less than square root of d and alpha is a constant. It's a kind of an asymptotic result. It depends on beta. And what is beta? Beta corresponds to my A. Everybody please. Beta corresponds to my A. What is my 0 corresponds to? Square root of d. All of you? The 0 is replaced by square root of d. My A is replaced by beta. Here, what is that we said? If A is 1, if A is 2, A is 3. Likewise, I can increase beta. If I increase beta, the breadth of that interval is larger, more mass is contained. If beta is smaller, the breadth of that is smaller, the amount is lesser. Nevertheless, it is always greater than 1 minus. And dependence on beta is exponential. How many of me? It's a very beautiful result. So what does this tell you? If I generate random numbers from a Gaussian distribution with unit variance, more likely you will get vectors whose lengths are concentrated around square root of d. That's a fact of nature. You didn't make it, I didn't make it. Nature made it. And why nature made it? It's a property of high-dimensional problem. And where does it occur from? Law of large numbers. Are you with me? That's right. That's right. Now you understand the importance of law of large numbers when you deal with large data sets. I think I have only 2 more minutes till 12:30. I have a few more slides. I don't want to be in a hurry. Especially, I have a topic which is of great interest to all of you. It's called covariance estimation. The covariance estimation high dimension. How many of you have done ensemble analysis, ensemble problem filtering? How many of you know how to generate ensemble covariance and everything else? How many of you want to work in ensemble analysis? You must all come tomorrow. Don't miss it. I'm going to be talking about the consequences of being able to estimate large covariance matrices in high dimension. And where does it occur? It occurs in ensemble column filtering. I'm trying to have an ensemble model for a large dimensional problem in meteorology, in geosciences. How many ensembles you create? 50 ensemble, 200 ensemble. What is dimensional is the space? 10,000, 500,000. So in a 500,000 space, you create an ensemble of 200. Why 200? Because that's all the time I have. It's not that I cannot create 10,000 samples. It takes more time. So how can you ensure the quality of the forecast covariance from a matrix whose text space is 10,000 long, but you have only 200 samples? Do you see the problem? How many of you see the problem, please? Come on, guys. I have a model. I have a discretized space. My discretized model in a computer runs with a state vector of size, let us say 10,000, 12.5 kilometers, monsoon data, the region west of Saudi Arabia, east of Singapore, north of Tibet, and south of equator. That's the region that affects the Indian weather. This region, if you discretize it at 12.5 kilometers, what is the number of data points you have? What is the number of grid points you have? You compute it. It's several thousands. Are you with me? That's the state vector. And that's at one time. I'm going to create ensemble of those state vectors in the ensemble filtering. How many ensemble have? 200. So you have a vector size 10,000. You have 200 samples. I have to compute the forecast covariance. You pray the Lord and do that, right? Can Lord help you? I'm going to show Lord cannot help you in this. Why? The problem is the challenges in estimation. And that's what I want to talk about. Because of time, I don't want to keep you holding. We are supposed to have one other lecture. The time has come. Maybe 1 or 2 more minutes we will steal. Are there any questions? I will talk about this tomorrow morning, better guy. What are the other impacts of high dimension? Which is some of you may think, oh gosh, we talked all mathematical problems. Why should I be worried about it? Anybody who is interested in simulation should be worried about this. I already given you examples. Anybody who is interested in computing the covariance matrix from ensemble should be worried about this. I'm going to give an example tomorrow. So absolutely relevant to us. Let me stop here. We will have couple of minutes for a couple of questions. Mr. Singh, please see if there is any question from the audience. That's all. Yeah.
Is it good to consider,
Louder. I want everybody to hear you.
so is it good to consider the high degree of freedom while doing the data?
By high degree of freedom, I'm assuming you are meaning large dimension, right? That's right. So these are the problem consequences of high degree of freedom. So I'm trying to bring you to become aware of something you often ordinarily don't think about, but hidden within the world of high degree freedom or high dimensional space. I'm assuming you are using the word freedom to represent dimension, right? That's right. High degree of freedom and high dimensional space geometric counterintuitive properties from 1, 2, 3 to D, how our geometric intuition fails when you go from low to high. Understand? I wouldn't say probably strongly fails. We need to understand the behavior. Why do we say sometimes fail? Gee, I never thought that the volume of a sphere can become 0. Understand? So in that sense, your intuition may fail you because we were not ready for it. But once you know it, it doesn't fail you. It's a fact. So what are the facts from high dimensional geometry that I need to be aware of? That's the contents.
How will you decide this dimensional stability?
Dimensional
Stability.
stability? What do you mean by dimensional stability? I don't have a choice, sir. You remember the Indian region?
Yeah.
Are you with me?
Consistency of the data.
But you have the Indian region. I want to discretize. Tell me the accuracy you want to have a model for. I read that your current grid length is 12.5 kilometers. Can you do 1 kilometer? Yeah, absolutely. That's what you want to do.
Our colleague has said
One,
that.
one second, I'm coming. Arithmina? That's right. So it is you who make the increase the degree of freedom because you want to have information about the final structure that happens. With me? Okay, go ahead.
So one of my colleagues at Pentagota, he has done the ensemble filtering at 110 kilometer resolution. That is actually T126.
But what is the size of the state vector?
So that actually consumes a lot of computation actually requirement actually.
Even
So
with that,
if
yeah, good. Go ahead, finish it.
Go from 110 kilometer to 12 kilometer resolution, if our ensemble filtering we do, we need a very, very big computer system actually.
When you do that, that's right. So his statements were quite right. From 100 kilometers to 12 kilometers means 1/8. 1/8 in one dimension. You are talking about three-dimensional space. So what is the increase in the number of data points? 8 cubed.
512
I
times.
mentioned. So 8 cubed times the percent size.
More than 500 times.
Whatever the number is. That's right.
So computer petabyte has to be
That's
increased.
right. That's right. That's right. That's exactly the problem. So there is a need for higher resolution. Higher resolution means larger grid points.
Requirements.
Larger grid points means a larger state space. When you are going to do ensemble analysis in larger state space, how many ensemble members you need in order to be able to guarantee good estimates of the forecast covariance? That's the question. What's the difficulty in Kalman filtering? The primary difficulty in Kalman filtering is the computation of the forecast covariance. I know mathematically, for linear system, I can do it precisely. It is not that I don't know, but the computation time is so large. I don't have machines to be able to do it in 5 hours, 3 hours, 2 hours. Are you with me? That's the reason we are generating teraflop machine, petaflop machine, exaflop machines. The impetus for generating newer computers essentially comes from geophysical sciences because I want to be able to do problems with a higher resolution. With a higher resolution, I want to be able to do the problem in my lifetime. What's my lifetime? 12 hours. Because I need to forecast, right?
Some lead time. We got some lead time.
Are you with me? So I'm going to talk about some of the challenges. That will be the first order of business tomorrow morning. And once I finish that, I'm going to go into the next topic called clustering algorithms. And we have applied clustering algorithms to several different types of meteorological problems. One is temperature distribution, another is rain analysis, another is multimodal ensemble. So I will give you those papers and I will also start talking about clustering algorithms as we go by. Any other question? One more question, please. If not, have a good afternoon. I will see you bright and early, 10 o'clock tomorrow sharp. Thank you all. Bye. Thank you.
Materials will be available in the whatever you're teaching that is available.
Of course. One is I will give you a copy of my slides, and then there are sources.
Thank you.
And if you there are different.
And for IIT.
IIT.
Yes.
Oh, IIT. Then you said, see, what I thought it must be related to space.
I am doing the prediction of multiple.
Oh, you are the monster. So I'm going to be also.
So one of the colleagues that I was telling about, he is now going to Hyderabad. But he was doing it in the LTK.
Thank you. Good to have you. Thank you.